Okie dokie. This is, I think, the last note that is necessary in this particular course, but I am actually going to do a couple more on matrices because when you're taught them in university or college, sometimes they are harder than they actually look. So know that I'll be redoing this again using a different method. Right now, I'm going to remind you that if you need these pictures, they are actually on the Google site, and I've dug it out. There's this version and another with, I think, a little bit of space. There's also the blank note. So this is all the different types of ways three planes can intersect, or I guess not intersect. So A, B, C, D, E, F, G, H. That's 8 ways that three planes can intersect or not intersect. And I'm going to go through each of them. This is a much longer note than it has been in the past, so I will take lots of hand cramp breaks. So each one of these requires a solution. So it is not a case of you looking at the equations and saying, oh, it's this. You have to say why you think it's that. So the first one, I'm going to move B out of the way, and we'll look at that in due time. And some of these will remind you of, or hopefully will remind you of, some skills or examples that we got in the intersection of two planes. So there we go with my first one. So this is when all three planes are exactly the same plane as each other. So they are, all three of them are parallel and coincident. So we did two planes being parallel and coincident. Now there's going to be a third plane that's parallel and coincident, meaning that they have an infinite number of points of intersection because they are all exactly the same plane. So what I'm going to do, personally, I need to do what I did in one of the examples of intersection of two planes, and that is I need to stack this information. So this is something I need for my particular eyesight. I like to keep things sort of on the up and down. So I do want you to know that this pattern of parallel and coincident is not always easy to just look at, which is why I'm saying you need some work. Okay, so I am going to compare everything to this, and this is very much scribble work. Eventually I'll come down here in blue and state my facts. So if I take this one, and I've chosen that one because it's got the littlest set of numbers, if I take that and divide it by 2, because I can, I will create 2x minus 3y plus 5z minus 4 is equal to 0. So that's a different version of plane 2 based on this calculation. And remember, I said it was scribble work. So if that happens, you get this. If you take this one and divide it by 3, because we can, 6x divided by 3, 9y negative divided by 3, 15z divided by 3, and negative 12 divided by 3. Oh my gosh, it's the exact same numbers as down here. And then I'm going to do it again here, because I can, only this time I'll divide by 5. And that will be 10x divided by 5, negative 15y divided by 5, don't fake any math, positive 25z divided by 5, and negative 20 divided by 5. And they all, when they're air quotes reduced, they all make the same plane. So what that means down here in blue, is I have just said that plane 1 is the same thing as plane 2 multiplied by some scalar multiple, which is also equal to plane 3 multiplied by some other scalar multiple. And you can pick whatever letter you want to put in here. You can't pick X, you can't pick Y, you can't pick Z, you can't pick M for direction vector, just in case you lose the hat. You can't pick N, those are all bad picks. I'm going to pick Q just because it's a nice letter. So we've got all three are scalar multiples. That means, and this is me just scribbling over here, that these are the same plane, only written 3 times in 3 different ways. And what that ends up meaning, back to the blue pen, the planes intersect, spelled properly, intersect in the plane. So it's not good enough to say that they intersect in a plane or intersect in the plane. You have to specify which plane it is. You could pick this one, you could pick this one, you could pick this one. I am going to pick the littlest numbers, again, that I've created 3 times. So they all intersect in that plane. So it's like all 3 of them are lying on top of each other and they just bang into each other at exactly the same point. So you've got an infinite number of points. Okay, time for a hand cramp break before I move on to part B. So second of 8 possible configurations. So I think I can get out B now. A couple of things I want to come back to with part A before I forget. Each of these questions will be to determine the intersection, if any. So if there aren't any intersections, like the next one is going to be, you have to state there aren't any intersections. If there are intersections, like there was here, then you have to state what the intersection is. Another thing is, you could be super specific if you are capable of being super specific. And that is, we could say that plane 1 is equal to plane 2 divided by 2 and then times by 3. We could say that plane 3 is the same thing as plane 2. Oh, that won't work. Hold on a second. Plane 3 is equal to plane 2 divided by 2 to create this, and then times by 5. So you can be very specific about these values as long as you're willing to state it in 2 statements. Okay, so moving on. Finally, part B. 2 planes are parallel and distinct with a third plane that is non-parallel. So that means this plane here, one of the 3, and this plane here, a second of the 3, would be parallel and distinct. So think about what that means when we went with 2 planes in the last lesson. And then a third one that has nothing to do with anything. Now if you take a look at this, the blue plane in my picture and the green one intersect, and they intersect in this line right here. And then the red plane and the green one intersect in this line right here. But all three of them don't intersect at all. So this is going to be a no intersection question. But first we have to prove why it's not an intersection, as in, let me try that again. We have to prove which possibility it is. So we have to prove that 2 planes are parallel and distinct with the third plane that is non-parallel. So I'm going to do what I did in the last question, and that is stack my information. So the first plane is 3x plus 5y minus 2z minus 4 equals 0. The second one, 4x minus 7y plus 6z plus 11 is equal to 0. And the third one, 6x plus 10y minus 4z plus 1 is equal to 0. So I'm going to call this number 1, this number 2, and this number 3, rather than calling them plane 1, plane 2, plane 3. So you have to state the pattern that you see if you see a pattern. And I see a pattern between 1 and 3. Actually, it's a semi-pattern, which is why they are the two that are parallel and distinct. So if I take a look at those two, blue pen, 3 times 2 is 6, 5 times 2 is 10, negative 2 times 2 is negative 4. So my normal for 1 is equal to 2. Nope, got that backwards. My normal for 2, not even 2, 3. Oh my gosh, stop doing this on Saturday nights when I'm tired. The normal for plane 3 is equal to 2 times the normal for plane 1. So I've checked out the letter parts of it. But you'll see that the D part of it doesn't work. So the D for 3 is not equal to 2 times the D for 1. And what that means is that we can say that plane 1 and plane 3 are parallel because of the normal business, but they're distinct because the D value is different. So that means we've got like the blue one and the red one. Now if you notice, this set of numbers has nothing to do with the first set or the third set. So plane 2 has absolutely no relationship of being parallel, distinct, or coincident with plane 1 and plane 3, and because of that, you have a case of there being no intersection. And again, I remind you that there is an intersection between plane 1 and plane 2, and there is an intersection between plane 3 and plane 2, but there is no intersection of all three at exactly the same time. So here is the third one. 3 planes are parallel and distinct. I'm going to take a hand cramp break, and then I'm going to move at the same time D out of the way so that I have some space for this and then go on. So the grand scheme of intersection of planes, or I guess intersection of 3 planes, the first 2 and these next 2 are on the, I'm going to air quote this, easy side. As in, you don't have much work to do to prove what relationship there is. So enjoy this while you can. I'm going to do this one a little bit different in case you need things spelled out a little clearer. I'm going to start the same way as I did before. So I'm going to write my plane 1 here. My plane 2. And my plane 3. And for me, again, personally, I look at this and I can see patterns a little more easily than I can when the information is written side to side. Now, something you might want to do, if it helps you, is to list kind of the criteria of the planes off to the side. So this might help you. So the normal for 1 is 1, negative 2, 3. That's the x, y, and z from the normal vector. And the d is negative 9. The normal vector for plane 2 is equal to 2, negative 4, 6, and the d for 2 is equal to 13. And the normal for plane 3 is equal to 4, negative 8, 12, and the d for plane 3 is negative 17. So if this is too much for you to look at, you might see patterns a little more easily when you take the letters out. So now that I've got all the letters out, I can see, let's see if I can write this down right the first time, I can see that the normal for plane 2 is equal to the normal for plane 1, but I'd have to double it. But I can also see that the d for plane 2 is not double the d for plane 1. So I have parallel and distinct between this one and this one. If I then look at 1, which has the little numbers, and 3, the normal for 3 is equal to 4 times the normal for 1. But if you look at the d values, that doesn't work. So the d value for 3 is not equal to the 4 times the d value for 3. Try that one more time. 1. So that means we have 3 planes that are parallel and distinct, meaning that they are all parallel, but they lie kind of one on top of each other, but not touching. So there's space in between all of them. They're sitting at different levels in space. And when that is the case, you get to say that there's no intersection. And this is why there's no intersection. Insection, not a word. Intersection, a word. All right, so if this helps, do it. If it doesn't help, don't do it. I'm going to do it one more time with the next one. So, example D, after a hand cramp break. Okay, I've just made the executive decision that this is my Saturday night and I'm tired and I don't want to do this. So I'm going to finish part D, and then what I'll do is I'll make a separate video, or maybe 2 separate videos for E and F and G and H. So you should enjoy this first video while it's still in action, because it's the nicest of the 2 or 3 that I will end up doing. So here's your picture. 2 planes are parallel and coincident, so this is like 2 planes stuck together. And then this one is parallel and distinct. So take a look, there's no intersection, but we need to prove that this is the situation before we can say there's no intersection. So I'm going to do the same thing as I did before, including all the extra. So x minus 3y plus 9z minus 18 equals 0 is the first one. The normal for the first one is 1, negative 3, 9, and the d value is negative 18. The second one, 2x minus 3y, 6y, plus 18z minus 36 is equal to 0. The normal for that is 2, negative 6, 18. So I can already see times 2 times 2 times 2. And d2 is negative 36 times 2. So I've already found my 2 identical, 2 parallel and coincident planes. More about that in a second. Third one, 4x minus 12y plus 36z plus 13 is equal to 0. And I can see times 4 times 4 times 4. Nope. Some of you might find it advantageous and a little less information without the letters. Might notice it easier here. So we have to prove the situation before we can say no, see if I can spell it right this time, intersection. So you can't just say that. I will not give you full marks for that. There is no teacher on the face of the earth that will give you full marks for that. You have to state the situation and why there is no intersection. So, as I said, normal number 2 is equal to normal number 1, but we doubled it. And D2 is equal to doubled of D1. So that means plane 1 and plane 2 are parallel and coincident. They are identical. Then I can look at normal number 3, which is the same as normal number 1 if I times it by 4. But D3 is not 4 times D1. So that means I've got plane 1 and plane 3 are still parallel because of this first business. But this makes them at different levels, so they're parallel and distinct. And because I have now proven that, now I get to say that. So the first 4 examples, and there's no order to this, it's just random, but the first 4 of my examples of intersection of 3 planes is, I'm going to say the easy ones, the ones that have the nice little pattern. So I'm going to stop here with this so the note doesn't go on forever and ever and ever. And I'll make a note on the Google site that says, okay, it's only the first 4, and then I'll indicate on the next videos which ones you're looking at with respect to this thing. Taking its time, taking its time, taking its time. So I will continue, maybe tomorrow when I wake up, to take care of all the other slightly messier ones. And I might take this more on this later and just keep motoring with it. So in a regular 75-minute class, this is, I think, a 2-day note. And now you might be able to see why. Anyhow, if you want to, just a reference, there's the stuff that you can attack in the red textbook. But as it is, I will move on with this later.